Okay, so good afternoon. First of all, sorry for not being in Rome, but it was impossible for me to come, so that's why I give this talk remotely. So after the HT-Cal talk, we are now looking even further into the future, and I will speak about the calorimetry for future accelerator experiments. And there is a recent R&D working group actually which has been started at CERN, and we are at the stage of proposing R&D in the field of calorimetry there at CERN, and I would like to introduce you to the different possibilities which we are studying at CERN. Okay, so the outline of today's talk is then general introduction, then for which future accelerator experiments we actually doing this development and this R&D, and so what does it concern? Then the proposed R&D at CERN, then in the calorimetry field, so there is some R&D planned for FCC-HH, for LHCb upgrade 2, and also for treatment CLD. Okay, so first let me really start with the European strategy. So 2013, the European strategy for particle physics declared the top priority to fully exploit the LHC, possibly until 2037 or so. I mean, this is not written in the strategy, but this is what you can see actually on this graph or on this picture on top of the slide. Where you can see the different phases of the LHC upgrade, and you can see that this tentatively goes up to 2037 to collect 3000 inverse femtobarn with high Lumi LHC. However, as a second point, and you see that in this screenshot on the right hand side, in green, so under the letter D, it is also mentioned that CERN should propose post-LHC accelerator projects and of course the detectors which go with it. And so today I will of course mainly concentrate on this second part. Okay, so you know that for the machine and for the experiments there are two upgrades foreseen, 2019, 2020, so this is just about to start. And 2024 to 2026, the so-called phase 2 upgrades of Atlas and CMS, and there we are in the stage of having finalized all the PDRs and going through the approvals at the moment. Next slide. So beyond that, then also R&D for the next generation of accelerators and accelerator experiments has clearly started. And now, in this talk, I will not speak about the accelerator R&D, which is ongoing at CERN, so you know all about this FCC-HH, FCC study group, which is producing a CDR now, and it has several flavors of FCC. You all know about that, and I'm sure there were many talks. Here I concentrate on detector R&D for this next generation of experiments. Okay? Good. So, we have already a quite strong CERN involvement in detector R&D for KIC, FCC-EE and FCC-HH, and also in the upgrade 2 of LHCb. So there is already some involvement. And recently the CERN EP department has launched an R&D program on new detector technologies. And you can see here a screenshot of the web page on the right hand side. So it's a little bit small, but if you want to know more, then please click on the link on the bottom of the page. So there, 8 working groups have been put into life, and they cover basically all different kinds, and also detector mechanics and some IC technologies, high-speed link software, and detector magnets. Okay, and all you want to know about it you can find on this web page here. There was a first workshop which took place at CERN in March, and there's a second workshop planned for fall 2018, and at that time we would like to also come up with a decision actually on which of the proposed R&D projects actually will be supported by this program. And in the following I will now report on existing and possible future R&D in the field of calorimetry. So this concerns now only the working group 3 on this of this EP F1 here. Okay. Okay, so for which experiments, so on which experiments we are thinking of? Yeah. So first of all, it should be post HLLHC, so that means it's after the phase 2 upgrade of CMS and Atlas. And this is also fulfilled by the LHCb upgrade 2, which is planned to take place within run 2, run 3, sorry. LHC run 4, sorry. Yeah. So the current LHCb E-type is a scintillator-led charge calorimeter of some 50 square meters. And there is already now for run 3, there is already an upgrade 1 actually planned to read 40 megahertz, to read out 40 megahertz. There is then this upgrade 2 planned for LHC run 5, yeah, so it's starting in 2031, so it's falling basically into the scope of this working group. And there the idea would be to exchange the electromagnetic calorimeter in the high occupancy belt region, yeah, that the operation becomes compatible with the luminosity up to 2 times 10 to the 34. Yeah. And they expect radiation doses of up to 3 megagray and 3 times 10 to the 15 particles per square centimeter. And what they will also need is timing information to mitigate the multiple interactions and bunch crossing, and while keeping very good EM energy resolution of the order of 10% over square root of E with a constant term of 1%. Okay. And on top of that, they want to reduce the Molière radius to 2 to 3 centimeters. So this calls for very dense absorbers like tungsten. And this, of course, also helps to improve the pile-up and to be able to better disentangle the different showers. Okay. They want to have fast response, and of course have to respect the dimensional constraints of the modules, because since they only exchange the inner part of in the high occupancy belt region, which you can see in the little sketch on the right hand side. So this is this orange stuff which they want to replace there. Okay, and this needs to fit, of course, in the other detector. Okay, so this is one of the scope. Then we have, of course, the click ILC helix, the detector for click and ILC, which are mainly, of course, followed by the CANDIS collaboration. So there, these calorimeters, they are optimized for particle flow. The radiation tolerance and bandwidth requirements are benign compared to LHC, but they have higher precision requirements. Yeah, so it's about 2 times for jet energies and 10 times for track momentum. So the big challenge is to have high jet energy resolution at the level of 3 to 4% for W's and Z's, because they want to separate W and C decays. And therefore, each particle needs to be, so one concept, of course, which can do that is the particle flow, where you basically reconstruct each particle, of course, individually, and use the optimal detector for each particle. So the tracker for charged particles, the calorimeter for photons, and the hadronic calorimeter for neutral hadrons. Okay? So this, of course, requires fine R&D, fine 3D segmentation, and they have different options, which you see on the right-hand side, on the bottom. But I won't go a lot into details here, because you heard several talks about ALICE already today. Then there is, of course, FCCEE. So there they have 2 different detector concepts. They also need excellent jet energy resolution, so this is very comparable, of course, with PIC and ILC. And they need some radiation tolerance and bandwidth, but it's also, of course, compared to LHC or even FCCHH, this is, of course, rather low requirements. But what is important is particle ID, of course, and also they need to be somehow optimized for particle flow or to have dual readout. So at the moment, there are 2 different concepts. I think you also heard about that already in the session today, earlier on. So there are 2 concepts: the ideal detector, which is building on dual readout electromagnetic calorimetry, and there is the basically click detector revisited C&D detector, which is building on a silicon tungsten high granularity calorimeter. And then last but not least, there is the FCC-HH, which of course has the worst radiation requirements. So this is a factor 10 to 30 times more than HF-LHC, which means for the calorimetry, this is something like 2 times 10 to the 16 particles per square centimeters, and in the end caps, and 5 times 10 to the 18 square centimeter in the forward region. So there, this is clear that silicon is probably not the choice for this, at least for the forward region. May be possible for the end caps. Of course it's high luminosity, so there will be high pileup, about 1,000 crossings per batch crossing, 1,000 events per batch crossing. Then the physics program calls for high ether coverage, because due to the higher proton energies, we have many more particles. So the light particles actually very often produced with a large boost, and therefore go more into the forward direction, and hence you need a calorimetry up to ether equals 6, at least for EVF jet tracking, and we also need precision tracking and precision calorimetry up to ether of 4. Then we want to have also high granularity, because this will help, of course, for particle flow, also to disentangle collimated final states, so like top quarks, which will end up in one jet cone. And of course it will also help for particle ID and pilot projection. And then on top of that we need high resolution, e.g. for example for Higgs self-coupling measurements, like with Higgs, the golden channel, Higgs BB, gamma gamma. And the hadronic constant term should be around 2 to 3%. Time resolution, of course, is essential to help with pilot projection. And then there should be somehow combined measurement with the tracker, because you will see later that the calorimetry alone cannot, with this huge pileup of 1,000 proton collisions per batch process. Okay, so there are several possible technologies. So either a highly granular EM calorimeter based on noble liquids, so lead, or also a silicon tungsten in the barrel region, but probably in the end caps forward we need some. And a hadronic calorimeter is foreseen like scintillator steel in the barrel, and noble liquids based also for the end caps. Okay, next slide. Good. So now, how does it work now with the R&D proposals in this framework? So you've just heard about the different future accelerator experiments, and now how did we basically try to group the different R&D proposals for this CERN R&D group. Okay, so we received actually about 20 different proposals for R&D at CERN in the field of calorimetry, and we basically grouped them in several, according to the active material. So first of all, and then propose several projects for each of those. Okay, so the first one would be an R&D proposal on noble liquid calorimetry. So this is, as you just heard, this is mainly focused at FCC-HH, and at CERN we would like to look into granularity of the readout electrodes and do that with SPICE simulations, and then do PCB designs, production and measurements, and timing optimization of the whole readout chain. We would look into Fick's rules, and also would look into the lab properties at such high ionization rates. So this will come later in this talk, more details. Then the second big group would be scintillator-based calorimeters. So as you have just heard, this is the one very interesting option for the LHCb HCAL upgrade 2, but also for the FCC-HH HCAL, for the FCC-EE HCAL, and also of course for Quick INC and also CEPC HCALs. Most of the HCALs nowadays are somehow scintillator-based calorimeters, and there are two different flavors. Some actually have now silicon PM sitting directly on the scintillators, and then there are some proposals like for FCC-HH, which are more atlas-like, where you have tiles which are read out with wavelength shifting fibers, and then only on the outside silicon PMs, which is of course in high radiation environments an advantage because you can easily exchange silicon PMs. Okay, I will also come back to that later in this talk, but of course you heard already many talks about in this session. And then there is of course silicon-based calorimetry. So there you just heard the previous speaker showed you this huge enterprise, these huge plans for the CMS HG tile. So this will be a huge and very challenging project. And there, of course, you heard already talks. And the question was basically for CERN, so what is the R&D which will be necessary after the HG tile is finalized, and then with the focus on other experiments like FCCEE or CEPC or ILC. Okay? So this was the big question, and there we came up with a proposal that we would focus on power pulsing, because this is important for the linear colliders, mainly power pulsing, and then of course other system aspects which are important for PIC and CLD e-pulse. Yeah? So CLD is the FCCEE detector, basically one option of that. So we would plan to build realistic modules, including sensors, electronics, absorbers, and holding and services. And I will shortly come back to that with a little bit more details. And then there are R&D proposals on ultra-low radiation length diostats, so I will not speak about that today, but this is of course interesting for, of course, noble liquid calorimetry, but also for all experimental magnets, which sometimes are in front of the calorimetry, and then of course it is crucial that they are ultra-low radiation length. So there is also some R&D proposal about carbon fiber diostats, which has gone into this program. Okay. For the moment, all those things are only proposals, and we expect a decision on the funding in fall 2018. So at the moment, I mean, we just wrote up what we think would be interesting, but this does not mean that this will really be done. It's all of that. Yeah. Okay. So let me start with FCC-HH. So I think you've probably also heard about that in the during the conference. So there is one reference detector which has been developed, which will be presented in the conceptual design review, which is due by the end of this year. And we have basically on this slide here you see the dimensions of this detector, and you see the proposed detector granularities and performance, the goals of the performance, which will be required for the physics program. Okay, so then on the next slide you see the big challenge also immediately, which is clearly the radiation. So the radiation requirements, as I said already, is about 10 to 30 times higher than for HLHC. So this is far beyond what can be done at the moment. So for the calorimetry, the only choice which we believe can survive such radiation is noble liquid-based calorimetry, at least in the forward picture. Yeah. So here you have the fluences. So for example, the electromagnetic calorimeter in the forward region is around 10 to the 7 and 5 times 10 to the 17 per 1 mega electron volt newtons equivalent per square centimeter. This is absolutely huge. Okay. Fine. So our plan for this FCC-HH was that we would combine the good intrinsic energy resolution, the radiation hardness, the high stability, linearity and uniformity, and the easiness to calibrate from an atlas-type noble liquid calorimeter, and combine it with basically the high granularity of something which is like the HG tile, which is proposed in CMS at the moment. So going down basically to order 1 square centimeter cells. Yeah. and which is important, of course, for particle flow, but of course also for pilot rejection and many other issues. Okay, and this was the idea basically to combine the two and propose a new FCC calorimeter. So on the next slide, you can see basically what this group came up with. So there is a reference detector which will be presented in this conceptual design review, and this consists of an ECAL which is lab-based and also an end cap and a forward hadronic calorimeter which is liquid argon-based. So this is very similar to the Atlas concept. Yeah? But the big difference is that this ECAL will achieve high granularity by multi-layer electrodes. So the big difference is, instead of the Atlas accordion, here the plan would be to have straight electrodes. However, these electrodes would be finely segmented into quite small delta phi regions and even finer strips. Yeah? So this is the plan at the moment, and these PCBs, the first calculations exist, and it seems to be okay for the noise behavior, but of course that tests need to be done, and this is exactly what went into this R&D proposal section. For the hadronic calorimeter, there are scintillators proposed in the barrel and also in the end cap, and scintillators in the barrel, and then this liquid argon technology, as I said, in the end cap and forward detectors. Okay. Good. So the ECAL performance, here you see the performance in the different eta regions on the left-hand side, and on the right-hand side you see the gamma peak for different pileup scenarios. And what you immediately see is that, of course, the resolution gets much worse with the pileup of 1000. And this has nothing to do actually with the technology of liquid argon here, but this is just because you get so much energy on top of your photons from the other collisions that no matter which calorimeter you would build, you would end up with such a resolution. So at the end, what you can see is that at pileup 1000, so this is the green curve on the right-hand side, the resolution goes up to 4%, 3.7% mass resolution of the Higgs to gamma. And this is basically only dominated by the pileup. So it's very crucial that we will have efficient in-time pileup suppression using the tracker, and of course also timing will help also, timing of the calorimeter will also help to suppress this pileup. But with not suppression, you see what you get. Yeah? Okay, so the proposed future R&D at CERN is, I will not read through all that, but it is, on one hand, is to develop further this high granularity readout electrodes. So there the idea is, of course, to design first electrodes, to spice simulation, and then build electrodes and maybe even small test modules. Then the second subject would be improving the timing resolution of such calorimeters and work basically on the limits of time resolution for noble liquid calorimeters, and how to tune the electronics to achieve the best out of it there. Then lab properties and performance under high ionization rates, so this would be measured in test beams. And then there will be R&D, as I said, on signal feed-throughs and low radiation length cryostyles. Okay, then for the H-file, there the performance has also been simulated. There the challenges lie basically on the silicon PM readout, which from off the late wavelength shifting fibers. This has not yet shown to work reliably for this kind of detector. So the proposed future R&D will be actually to show that, to profit from the Atlas Tile setup, which we have at CERN actually, and Tile lab to do these tests. Yeah? Okay. Good, so I think I will come now to the click detector, ECAL, and this is also for CLD, for FCCEE. Okay, so there, well, as I said, I mean, this, of course, they will mainly profit, of course, from the development from the CMS HTCAL project, yeah, but the idea would be to work in parallel on a continuation of calorimeter R&D for PIC and CLD, And so the important aspects will be the power pulsing, yeah, and some engineering, mechanical electronics design studies. Because the big difference to CMS HG is clearly the power pulsing, which enables larger effective density of the calorimeter and more compact particle showers, because we don't need active cooling of the sensors inside for a click for these power pulse click sensors, but you only need cooling of the electronics the outside, hence the whole calorimeter becomes more compact. So this some R&D effort will go into that. So this is one proposal. And then last but not least, there's this LHCb ETAL upgrade. So I told you already how the LHCb looks at the moment. So they have Schachlik modules, and the innermost region they want to exchange. So let me come to, so on the next slide you see the different steps of the upgrade. So the upgrade 1 will happen already for 3, so this is what they're preparing at the moment. But the upgrade 2 will only be in 2031. Okay. So the next slide, the overall requirements, as I said already, are huge radiation doses up to 3 megagray and 3 times 10 to the 15 neutron, 1 mega electron volt neutron equivalent per square centimeter. And you see on the little plot on the right hand side that this is of course quickly decaying. However, in the innermost region you need extremely radiation robust calorimeter. So there, plastic scintillators, for example, as they are used at the moment for this Schachlik calorimeter, are not an option. So they are now looking into either crystals, yeah, or other technologies. So this is on the next slide. So the options are homogeneous crystal calorimeter with some longitudinal segmentation. Yeah, so this would be one option. However, also other sampling calorimeters would be an option, like Schachlik or Sparkle type, but of course not with plastic scintillators, but here with crystal fibers or with crystal scintillators in the Schachlik calorimeter. Okay. So there R&D will need to look into radiation hardness of the crystals, but also of the light guides and the fibers, and then of course also into a radiation hard photodetector. And all that combined with very fast timing of the order of 20 picoseconds, which they also need to mitigate pileup. Good, so R&D has started on some radiation scintillators like the GHG crystals and also of gallium arsenide photodiodes. So the planned proposed future R&D you see in this little box on the right hand side. So it is the assessment of the radiation hardness of scintillator detector materials. Then of course the tests with silicon PMs operated at lower temperatures, because this might be necessary due to the high radiation. So there will be tests with different temperatures. And then the third big subject is clearly timing, how to optimize the full detector readout chain with respect to timing from the light production to the light guide to the photodetection. Okay, so that brings me to the conclusions. Okay, so you see that CERN got a clear input from the European strategy in 2013 that apart from operating and fully exploiting LHC with the HL-LHC project, we should also propose post-LHC accelerator projects and detectors with it. And for this detector R&D, has already started. R&D on CLIC, FCCHH, FCCEE, and FCCEH accelerator and experiments have started. And now today I spoke about this EP program, which has just been launched and where proposals have been submitted. In the field of calorimetry, there are basically 3 groups of proposals: global liquid-based, scintillator-based, and silicon-based calorimetry. And there will be a decision in fall 2018 which of these projects will actually be pursued and supported. And so, as you have seen, the R&D has already started. And we are, of course, very, very open for collaboration, and we hope to collaborate with many of you. Thank you.
Thanks so much, Martin. And let me remind that we also proposed an R&D for with dual readout, and we are also open to collaboration, and say. Okay. Any other question?
Here because you covered it in your talk. So the dual readout is one proposal inside the CP database calorimeters, and so there dual readout could be taken up on board, but this is under discussion at the moment.
Okay, thanks so much. Any question, comments?
You actually said decision will be taken in fall, but actually, which are the input that are required from our community to push the proposal? So to whom do we have to speak? Or what do we have to do?
Yeah, I mean, well, the thing is, I mean, this is now in the hands of the steering committee of this R&D, for this R&D project. And you can see actually the members of the steering committee on the page, which I put on my side 3, I think. So the steering committee basically prioritize the different projects which have been proposed. You see, I mean, in all the days working groups, there are many, many very good ideas, and if you add them all, this of course exceeds by far the available budget. Hence, there must be some choice which has to be taken, and yeah, so it's the steering committee which
is the steering committee the ensemble of the conveners, or is something else?
No, it's when we conveners, we gave our input, so this is basically what I just presented. But then this will be discussed, because the thing is, I mean, of course, each convener knows when it's its own field, however, the other 7 fields are not very well known. So, I mean, this will be basically by the division management also, department management of the CERN department. Plus these advisories and already many discussions also with future customers, so let's say FCCHH, FCCEE, GIG, INC, CBC. So this is the department now.
Any other question, comments? Franco?
How big of a budget do you envision for these projects? And also, I assume that you are expecting also some co-funding from also other agencies besides CERN. That should have an impact on the decisions, not only the CERN budget, isn't it?
Yeah, well, I mean, yeah, the budget is clearly limited. I don't want to really give details now about how much it is and so on, but it's clearly limited. And of course, yes, there will be collaboration with other institutes. However, I think there was also some feeling that CERN should concentrate on R&D, which is otherwise not covered. So that means, of course, collaboration with other institutes is very encouraged. However, if something is already very well covered in other institutes, it's not necessarily the best place for CERN to invest money, because we would like to basically make sure that all different technologies are basically driven to a point that we can write our next 3 hours basically and for future experiments.
Other questions, comments? If not, thanks so much again, Martin. See you in CERN.